Okay, so the next session will be about data at full tilt, accelerating discovery with wearables and smartphones. I'm the first speaker. My name is Daiqi Gao. I just wrapped up my postdoc at Harvard. I've been working with my postdoc advisor, Professor Susan Murphy, on mobile health and reinforcement learning. And mostly I worked on a clinical trial called Hard Steps, which aims at helping users increase and maintain physical activity. This is also what I'm going to talk about today. So let's get started. Can you guys see my slides moving?
Yes, we can. Thank you.
Thank you. Okay. So today I'm going to talk about optimizing intermediate outcomes for better long-term health using reinforcement learning and causal reasoning. This is a joint work with my advisor, Susan, our domain scientist in human-computer interaction, Peja, and several other postdocs and undergrads in my lab. So mobile health use mobile devices to help monitor and manage users' health. It is shown that it's effective at providing ongoing support for users in their everyday life to help them form a healthy and balanced lifestyle. For example, it could help patients with cardiovascular disease to reduce cardio risks and mortality. In this talk, I will mainly focus on using mobile health to help users increase their physical activity. And Hard Steps is such a digital intervention for physical activity. It contains multiple components. The first one is the walking suggestions, which encourage users to engage in short bouts of physical activity. And it targets users' affective valuation, which means that what's the user's gut feelings towards physical activity? Is it positive or negative? The second one is the salience message, which captures users' attention to highlight the benefits of physical activity. And it targets users' affective attitude, which means what do you believe about physical activity? Is it going to be beneficial to you? And the third one is the reflection and goal setting. In this talk, we will mainly talk about how to optimally send walking suggestions to users. Notice that there are two sources of heterogeneity. The first one is the evolving needs of a user. For example, if a user has already exercised today, then there's no need for us to remind them to take a short walk. But if based on our passively collected sensor data, we know that they haven't exercised today, then it might be helpful for us to send such a notification. And the second heterogeneity is across users, which means the different user behavior pattern. Even if two users both haven't exercised today and just received a walking suggestion, they may still react differently. Therefore, we will need a personalized policy for each specific user, and this policy decides at each decision time whether we should send a walking suggestion or not. Currently, the content of the walking suggestion is rule-based, decided by our domain scientists. And the goal of my team is to find the optimal timing of intervention. Specifically, we use online reinforcement learning to decide whether we should send push notification or not. We sequentially interact with the users to update the policy. And online RL is necessary when offline data is insufficient. There are some common challenges in mobile health. First, the user behavior are usually noisy. And second, as we mentioned before, the heterogeneity across users are usually significant. So this requires a significant amount of data to learn the signals in user behavior pattern. But in the meantime, especially when we are trying to use mobile health clinical trials to learn such signals, we only have limited user-specific data. Like each user may stay in the trial for like at most 9 to 12 months. And we only have like 2 to 5 possible decision times per day. So that's why we use domain knowledge and previous data to improve sample efficiency. Sample efficiency means how well an algorithm can learn with a limited amount of data. Here in the hard steps example, the domain knowledge refers to the behavioral theory. We embed such theory in a causal directed cyclic graph. The edges in the DAG represents the strongest causal relations among all the relevant variables. Then the conditional independencies implied by the DAG will serve as the assumptions in the RL algorithm to help us improve sample efficiency. For example, the causal DAG might tell us what is the optimal state reward construction or algorithm design so that we can improve sample efficiency. And the previous data will be used as the prior in Bayesian methods to warm start our algorithm. In the previous implementation of hard steps, the reward we use in the reinforcement learning algorithm is just the short-term step count after the intervention. However, the health outcome that we care about is actually the long-term behavior change. For example, if a user still keeps the healthy behavior after a year or not. But such signal is just too sparse for us to use in the algorithm to update the policy. So that's why our science team decides to use the intermediate outcome as the reward in the algorithm. This is defined as the affective association with physical activity, which is a combination of affective valuation and affective attitude. Based on the behavior theory, we know that the interventions affects the intermediate outcome through the proximal outcome, and then the intermediate outcome is also a mediator of the distal outcome, and it's a strong predictor of the distal outcome. So we know that if we try to increase the affective association with physical activity, then it's highly likely that we also going to increase the distal health outcome. Since this intermediate outcome is the measure of the user's intention, it can only collected from surveys. For example, it can be collected once per week on average, and it asks users what are their feelings about exercise, etc. This is a simplified example of the causal DAG that we use. The reward is defined as the daily affective association with physical activity. There are 5 decision times per day. Based on the current context, the RL agent decide whether a walking suggestion should be sent or not, and then it affects the reward through the proximal outcome, which is the short-term step count. And in the meantime, if excessive notifications are sent, then the user might just get annoyed and disengage from the interventions and the app. So the negative effect of the actions might go through the engagement, and it will affect the effectiveness of future interventions. So there are multiple challenges in this problem, and I will briefly introduce 2 of them. So this causal DAG is extracted from the previous figure, and the problem here is that we have a bagged decision times problem. Each bag here represents a day, and it contains 5 decision times. There's 1 action at each time, but only 1 reward at the end of the bag. The key assumptions here are that the bottleneck variables R and E separates the history and the future. And we generally assumes that the structure of a bag is the same over time. Our goal is to maximize the cumulative reward over the long term. The challenge here is that the transitions from variables to variables are non-Markovian and non-stationary. It's non-Markovian because all the 5 actions jointly impact 1 reward. And it's non-stationary because the information that we can use to choose the interventions will be different within a bag. So our first step is to discuss how to optimally construct the states so that we can have Markov transition and reward function based on this state. One way to do that is to define the state as a dynamical Bayesian sufficient statistic. Given this statistic and the current action, all the future rewards should be independent of the history. And this conditional independency can be read off from the DAG using the D-separation rules. Here we list the two possible debus that guarantees Markov transition and reward functions. Notice that the state depend on the decision time index k, so that's why it's called dynamical, because it's changing over time. And however, there are also other states that have Markov transition and reward functions. So the problem is which state is the best. There are multiple criteria that we can consider. The first one is the true optimal value function, which means that if we have infinite amount of data, what is the optimal value function that we can learn? We were able to prove that the optimal value function based on a sufficient statistic is no less than that of other states. For example, in the hard steps, S is the dbus and S hat is not. S uses the mediator or the proximal outcome, the short-term step count, but S hat directly uses the context. So using the mediator M instead of C will potentially generate a higher optimal value function because the mediator lies on the causal path from the context to the reward. So using the mediator will help us reduce the noise on this causal path. The main takeaway here is that when we are designing an experiment or a clinical trial, it is helpful to identify mediators, which could potentially help us construct a better state and yield a higher optimal value function. Another criterion is the learning variance when we only have a limited number of samples. And the takeaway here is that the sufficient statistic with the minimal dimension will have the smallest learning variance. So in the hard steps example, the first one S is better than the second one S check, even though they are both sufficient statistics. Now the only problem is how do we handle non-stationarity within a bag? Luckily, we have a framework called a periodic Markov decision process. Here, the period length can be equal to the bag length. It still requires Markov transitions and reward functions, but it allows non-stationarity within a period. The optimal policy will be a series of k different policies. Each one maps from its own state space to the action space. So periodic MDP naturally handles non-stationarity. Finally, we adapt any value-based RL algorithms for stationary MDP to bag decision times using the Bellman equations for periodic MDP. Okay, let me just quickly motivate another problem, which is active query. The challenge here is that remember the reward is obtained through survey, but this put burden on the users. So what we do is to add another action, a query action that decides when should we query user and when we not. For example, if the users if we based on the passively collected data, we know the user's behavior hasn't changed much, then there's no need for us to query. So when a query action is sent, we get to observe the true latent reward. But in the meantime, it will reduce the user's engagement. So the query action reduces engagement, but it helps us understand the transition and reward function. Besides, it provides an accurate state when choosing the intervention. We also formulate the problem as the periodic partially observable MDP. Here, the latent state will be our reward, and now the reward has two emissions. The passively collected data from the sensors, and sometimes the true value of this latent state, because we can sometimes query the users. The bag length will be the number of decision times plus 1, and this 1 corresponds to the query action. Okay, so to summarize, our goal is to improve the long-term healthy behavior of the users. The reward in the RL is defined as the intermediate outcomes, like effective association with physical activity. We use causal DAG to incorporate domain knowledge to increase sample efficiency. And finally, we use periodic MDP or POMDP to handle back the decision times and active querying problems. Thank you.
Thank you. And due to being short on time, we will take questions in the chat at another time and move on to our next speaker.
I think I'm the next speaker. My name is Irina Gaynanova. I'm associate professor at the Department of Biostatistics at the University of Michigan. Can you see my screen?
Yes, we can. Thank you.
Excellent. So thank you to Sarah for organizing this session. Today, I would like to talk about our work on thresholds for wearable device measurements. And I would like to acknowledge that this work is joined with Junior Park, who is postdoctoral researcher at the Department of Biostatistics at Michigan, and Neo Cock, who is a master's student in health data science. And we do have a preprint on arXiv in case you're interested. So this work has been motivated primarily by continuous glucose monitors, which are small wearable devices depicted here, and they have a tiny needle that can measure glucose levels every 5 minutes. One of these monitors typically lasts for 10 days or 14 days, and these are the most common models currently used in the US. This is an example data for one of these continuous glucose monitors for a person who has type 2 diabetes. This is roughly 10 days of measurements. So you can see that the glucose values range from roughly 70 milligrams per deciliter to somewhere about 250. And high glucose values in diabetes lead to nerve management. So these devices are commonly used to control the glucose levels. And the red lines over here correspond to the consensus thresholds of 70 to 180 milligrams per deciliter. It's considered good to spend as much time as possible within this range and not go above or below. All right. So in general, when we look at the wearable data, it's actually quite common to summarize it using fixed thresholds like illustrated before. So in actigraphy data, for example, it's typical to separate it into time spent sedentary or light activity, moderate activity, or vigorous activity. For the CGM data that I'm using as a primary example, as I have shown you on this graph, it's typical to divide all of this data into 3 ranges, which is percentage of time in range or in target between 70 to 180, and then percent spent low, which is called hypoglycemia or low glucose, and percent spent high, which is hyperglycemia. And this percent of time spent within fixed ranges is a summary metric that is commonly used in clinics and in research and in various downstream tasks. So it can be used as an outcome or as a covariate. In general, these thresholds for CGM are considered consensus thresholds. So there is an international consensus paper by Batalina where they recommend using these thresholds to have endpoints for clinical trials with CGM data. And in addition, when looking at the high glucose levels, sometimes it's further differentiated into level 1 and level 2 using an additional threshold of 250. And when looking at the low glucose levels, it's also sometimes additionally differentiated into level 1 and 2 using an additional 54 milligrams per deciliter. And typically, when summarizing this data using threshold, a treatment goal is to have as much time as possible in this green zone in range. And just for relative comparison, for individuals without diabetes, you typically spend about 95% or more time within the green zone. So generally speaking, this CGM data either have 5-number summaries if you have a more detailed thresholds, or if you combine the levels, you will have a 3-number summaries in range, percent above, percent below. And the question we're asking here, are these thresholds optimal? So this specific numbers, 54, 70, 180 to 50, should we always use these numbers across different populations? Should this be the same thresholds for type 1 diabetes versus type 2 diabetes versus gestational diabetes? And so what we're trying to do here methodologically is to try to define what does it mean for the thresholds to be optimal, and also have a methodology for finding data-driven optimal thresholds for specific population. So this search of CGM thresholds has actually been going on for some time, and this is just some evidence from the clinical literature that suggests that thresholds may need to be adjusted. So in particular, 70 to 180 is the current consensus time in range threshold that is often adjusted to the time in tight range. So the 70 is kept fixed, but from 180, it's moved to 140, in particular for diabetes during pregnancy. So this adjustment already suggests that different populations, in this case, diabetes during pregnancy, may need different thresholds. There's a recent work that demonstrates that depending on the threshold choice, one may have different interpretation of treatment effects, which means the choice of the thresholds may affect downstream tasks and statistical power. And more recently, in general, there is a line of work to use the full distributional representation, including some of the work by our group, but one can argue that this threshold-based summary is very simple. It's much easier for clinicians and the patients to interpret what the summaries mean, and they also current norm and regulatory side. And there's some work that we found in the statistics literature that's using and data-driven thresholds choice, but that's with a supervised setting. In our work, we're trying to focus on the unsupervised determination of optimal thresholds. So going back to this threshold problem, the way we are going to view it as histogram amalgamation, and I'm going to illustrate a little bit more what I mean by that. But basically, currently, the consensus thresholds, which correspond to this specific glucose cutoffs, are either F3 number summaries, so low, in range, high, which sum to 100%, creating a compositional data, or the full representation is a 5 number summaries. So you either have 2 thresholds or 4 thresholds. And we are going to view this problem of selecting what those numbers should be as a problem of amalgamating the histogram. So more specifically, if we look at the one person's data, all of the glucose measurements, this is the histogram. So they have certain percentage of measurements that are exactly at 30, at 45, at 50, at 70, and so forth. And when we look at the consensus thresholds, we basically look at the percentage of time spent within this particular ranges, which means we combine the bins corresponding to the certain area of a histogram. And for the CGM data, it's only taken integer values. So there's always a finite number of bins, and it's always in the range from 40 to 400, which is a device measurement range. But we can extend methodology more broadly that it doesn't have to be integer values. So more specifically, what this means is that now if we have one person, so this is a histogram, we want to create data-driven thresholds that I'm calling T1, T2, T2, T3, T4 that represent this histogram by amalgamating the bins within the threshold choices. And we have now n empirical histograms for n subjects, and we want to pick the optimal cut points T, so they're the same across the subjects, so that we provide this particular amalgamated version of the original histogram. All right. So how we are going to do that and what's going to make it optimal? So the idea is quite simple. So coming back, we have our original histograms, the fine-grained glucose measurements. And depending on the choice of threshold, we have an amalgamated version. So the basic idea is that we want this amalgamated version to be as close as possible as the original. We wanted to preserve the distance. And this is the idea of the distribution preservation loss. So using our original distribution of glucose values and our threshold selection, we want to minimize the average distance across all of our subjects. The second loss that we can consider is rather than trying to match the original distribution as good as possible, we're trying to preserve relative distance. So the idea is that if we have subjects I and J, that the original distributions looked very different, then the amalgamated version, we want it to look very different as well. If the original distribution was close, we want the amalgamated version to look close. And then once we selected how many thresholds we need, which is K, we can define the optimal choice of this threshold as the choice that minimizes this distance. And the question becomes, what is the right distance to pick? Because we're looking at the histograms and we're looking at the distributions, we're going to use the Wasserstein distance, which is an optimal transport metric between two probability distributions. So specifically, it takes into account the geometric structure of the neighboring bins. And for one-dimensional distributions, the Wasserstein distance can be expressed as the difference between the quantile functions. And just to give you a very quick illustration of what is happening. So suppose you have one density function at 1 and you have another density function at 3. And so what the Wasserstein distance would do is to move from one to another. It slowly moves this peak from left to right rather than trying to divide the mass across. So because the Wasserstein distance can be expressed through the quantile functions, we have the original empirical quantile function for our original distribution. And now we have the amalgamated version based on the thresholds. And basically what we need to figure out is what is the quantile function corresponding to this amalgamated version. And it turns out that it can be viewed as a linearization of the quantile. So here's a toy example. Suppose we have a histogram that has 1, 2, 3, 4, 5, 6 bins, and we're trying to amalgamate these pink ones. Then the corresponding quantile functions is depicted here, and the process of amalgamating the bins is equivalent to the linearization of this red line over here. So basically, when we're amalgamating according to the thresholds, we're just linearizing the quantile functions, and the choice of the threshold influences where this linearization takes place. This linearization can be expressed in closed form through the thresholds T, giving us the final optimization for the loss one. We're trying the new quantile to be as close as possible to the original quantile. So we're trying to figure out what is the optimal linearization. And for the distance preservation, we're just trying to preserve relative distances across the quantiles. This is a pretty challenging optimization problem. You can solve it using greedy approaches where you sort of agglomerate those bins sequentially one at a time. But we also developed a joint optimization approach where we can find all the thresholds at once, and the details are in the paper. And finally, we also have a semi-supervised generalization. So you can possibly fix some of the threshold choices and just optimize the others. The exciting part, I think, is the data application. So here I'm going to show you an illustration on two data sets. One is on 168 subjects that do not have diabetes, and another one on subjects that have type 1 diabetes. They had both Dexcom G4 CGM with 5-minute measurement frequency, and they're both publicly available. And basically what we're going to do is we're going to try to figure out data-driven thresholds separately for each data set because they represent two different populations, and compare their representation with consensus ones. And then we're also going to combine the two data sets together and see how data-driven thresholds can provide discriminatory power compared to the consensus thresholds.
You have 1 minute, Irina.
Oh, great. So let me show you first what it looks like for subjects without diabetes. So this is the original empirical quantiles. This is the discretization with our thresholds. This is the traditional ones. And I guess the point is that visually, hopefully you can see that the data-driven thresholds preserve the shape of the quantiles much better than the traditional ones. And the data-driven thresholds are lower than traditional ones because they are better reflecting this population. Subjects without diabetes have lower glucose values. I'm going to skip the type 1 picture and just going to show you the discriminative power. So each of the vertical lines is a bar plot of 3 number summaries where we start with individuals without diabetes and then go to individuals with type 1. And what you can see is that there is a difference between left and right for both traditional thresholds and data-driven one, but the difference is much more dramatic for the data-driven thresholds, which happen to be higher in this case. And if we look at the classification accuracy for each of the threshold choice, we have almost perfect separation between subjects without diabetes and subjects with type 1, where the traditional thresholds only have a perfect separation at the top bin, but not at the bottom two. So highlights, we introduced loss-based threshold optimality to summarize data from wearable devices. And these summaries are easy to explain and they can be used in standard downstream tasks. It's on a supervised threshold determination, so downstream tasks are not going to be affected because we're not double dipping, we're not using the outcome and creating these thresholds. And there's a lot of flexibility because we have a semi-supervised versions. There are some challenges like how many thresholds I should pick. Currently, this is driven by existing clinical considerations, and also trying to adjust for hypoglycemia, low glucose values in CGM contexts may be of interest. And thank you for your attention. If you want to learn more, this is some of the references.
Thank you so much. That takes us to our last speaker for the session. Wonderful. So Dr. Haochang Shou from UPenn is here to wrap up the session.
Awesome. Thank you. Let me share my screen. Can you see my screen?
Yes.
Great. All right. I want to take the opportunity to thank Sarah for organizing the session, and I appreciate the opportunity to speak with many excellent fellow female statistician and data scientists. So today I want to talk about a work that we have been doing, harmonization of time and physical activity intensity measure from multiple sources or devices. I should mention that this is also a work led by an awesome female statistician, Dr. Jinru Zhang, who was one of my former postdocs, together along with my colleague, Dr. Hongzhe Li at Penn, and then Dr. Urjatri at the University of Minnesota. So needless to say, this is a wearable session. We're aware of the exciting opportunity and challenges that were introduced by the advanced development of multiple types of wearable computing sensors. One of the most commonly used devices is the actigraphy or accelerometry data for measuring physical activity and intensity movement. Irina has also talked about the glucose monitoring, and there are many other types of devices that can measure the sort of biosignal while we're in the free living conditions. So my research still focused mainly on the accelerometry data, which range from sort of research grade to sort of commercial grades, different devices, but they all allow sort of passive or objective assessment for physical activity intensity in a high frequency domain. They can be attached in various body positions in wrist, hip, ankle, or thigh. And depending on the study designs, they could record high frequency measurements of motion from 30 to as high as 100 hertz. And usually those data are being collected repeatedly across multiple days or weeks or even months. So why are we studying physical activity? I just want to throw out some health benefit statistics saying that while we all recognize there's a huge health benefits of physical activity physiologically or mentally as well. And WHO has mentioned that insufficient physical activity has becoming the fourth leading risk factors mortality. There's a recommendation about us taking about 150 minutes of moderate activity each day and 2 days of muscle strengthening activity each week. So this sort of talks about the importance of enhancing the physical movement and understanding physical activity pattern in relationship with our health outcome. And usually, however, the device is not directly giving you those metrics of moderate to vigorous activity intensity level or step counts. Instead, what it's actually measuring is a high-level time-varying physical activity level while we are doing certain positions or doing exercise. So here I'm just showing examples of the physical activity data from one particular participant across 4 different days. And these are mini-level activity counts, meaning that they are being processed and measured into 1 minute per value. They don't have a specific unit, but the level just talks about the magnitude of movement. So as you could see that the data gives us a lot of challenges, including the sort of high dimensionality, high temporal variability, and also between multiple days of measurements, there could be a lot of correlation that we need to account for. One of the challenges, though, that sort of stop us from directly applying or using the physical activity as a directly usable or reliable sort of a phenotype or clinical endpoint is there are a lot of the variations in the type of devices that are being used in the studies, the body placement of the devices, and then processing algorithms. So here are just a few examples in the literature that demonstrating with different studies that are available, oftentimes a different type of manufacturer of the device has been used, or even within the same brand, there could be multiple processing algorithm or threshold decision that's being made that might lead to big variations in the outcome that we're interested in studying. So our goal is to try to identify the existence of such variations and see if we can help address some of the discrepancy that's due to technical variability. And I wanted first to convince you that this is an issue even within a single study. So here we look at the data coming from the US National Health and Nutrition Examination Survey or ENHANCE study. This is one of the largest sort of a survey study within the United States conducted by CDC, and it has a whole array of different metrics, including the physical activity metrics that are assessed by accelerometers. So within the ENHANCE study, there are two different cohorts of activity data available. The first one was taken between 2003 to 2006, where the Actigraph uniaxial device called AM7164 was used, and these are the hip-worn devices that generate uniaxial one-dimensional activity intensity metrics called activity counts. Later on, another cohort of physical activity was taken using a later version of the Actigraph device called the GT3X. So this is a wrist-worn devices and that has 3 acceleration measurements. And in the efforts actually trying to push the transparency and reproducibility of the metrics, the MIMS or the Monitor Independent Movement Summary was processed as the activity intensity metrics. So it's a different metrics that are supposed to be device ignorant. However, it was different from the early cohort. And then I'm going to show you later on that there is some differences between these two. So here I'm just showing within the ENHANCE study between the two cohorts, the average activity counts intensity value from the early cohorts versus later cohorts. On average, the pattern looks quite similar, despite the magnitudes actually differ quite a bit. And in this study, we also calculate the temporal covariance patterns between different time points. And this is a heat map showing the average difference between the early cohorts minus the later cohorts. Here we can focus on this first panel showing that within each day, the temporal correlation actually differ quite a bit. So this could be a problem because in looking at the time varying activity intensity values and the pre-processed pipeline, the temporal correlation could matter quite a bit. So we were looking into how can we help addressing and removing such variability between two cohorts in the ENHANCE study. Some of the data characteristics that we need to keep in mind is, as mentioned, that the data are highly correlated between different time points within the day, as well as across different days. Every subject has multiple days of observations. And one thing I want to mention is we are dealing with a scenario where the two cohorts, they're not paired samples, meaning that it's not the same amount of subjects or same group having two devices were side by side. So it's not just a calibration problem, but at the same time, we also need to make sure that we adjust for possible confounders and covariates in the different population. And then lastly, we wanted to handle the temporal covariance pattern contained in this type of data. In the literature, there are a couple of methods that can be used for sort of a complex data harmonization. Here are our competing methods that we kind of compared with. The very simple ones was just a normalization step where we simply calculate the variability across all the data metrics and trying to do a z-scoring type of standardization. We also compare with quantile normalization, which essentially is matching the histogram of the physical activity intensity between the two cohorts and then trying to make the distribution look similar. However, those sort of methods does not respect the temporal order of our data, so this is less ideal. I personally also work in harmonization problem in other data type, including neuroimaging data. So in neuroimaging world, we have achieved quite a bit of success in proposing a methods called longitudinal combat or covariance batch effects correction methods. To put them in the contents of physical activity data, the longitudinal combat can be modeled in the following equation. So suppose the Y is the physical activity intensity time t for subject I and on day j coming from a specific cohort A. Then we model them as a sort of relationship with the mean activity intensity level for this particular subjects. The relationship that can be handled and accounted by biological covariance Z beta. And then we allow for subject-specific random intercept, and also the red parts contain the sort of variability that we think are attributed to the cohort-specific or device-specific variation. So we wanted to estimate the gamma and delta and try to remove that from original data. However, this method is not specific handling the covariance differences, but rather doing this time point wise. So again, this is not the most ideal cases. And as the previous result as shown, using longitudinal combat, we actually was not able to remove the covariance differences between cohorts. So this leads us to the development of our methods called INTAC. It stands for the integration of time-varying data from wearable sensor for physical activity intensity. Essentially, this is our model, which is similar to previous longitudinal combat model. The only difference is in the IDA, the residual term, where we try to further decompose them using principal component type of analysis. So essentially, we decompose the IDA IJ into using multi-level functional PCA type of methods into the subject-specific components, day-specific components. And then we assume that within each latent component, there is a rotation in the functional principal component eigenfunction, as well as a scalar differences in the eigenvalues. We try to preserve the common latent functional principal components while estimating the source-specific rotation and rescaling, which is the U and D matrix here, and correct from that. So in the interest of time, I'm not going to talk too much about the detailed implementation. We essentially optimize this subject-specific estimates of the covariance pattern with respect to such decomposition. And then afterwards, we try to correct the original data by preserving only the common shared latent components, but removing the source-specific rotation and rescaling factors. We also propose a matrix for choosing the number of eigenfunctions. So here, instead of just looking at the proportional variation explained by the principal components, we also look at the balance with looking into the similarity between the two different sources. And the underlying thoughts was if they are very different between the two cohorts, then we probably don't want to harmonize them as well.
We're out of time.
Okay.
If you could please quickly wrap up.
Sure. Yeah.
Thank you.
Sorry about that.
We don't have any additional time. We have another session that's beginning now. Thank you very much.
Okay. I'm sorry about that. So
please show your concluding slide so we can contact you with questions.
Sure. Yeah. So I think the concluding, I would just show
just show the slide, please. Thank you.
Okay. Yeah, I will show this one slide showing that our